everybody, welcome back to your Gregorius Maths video. In this video we're going to embark on a very important algebraic topological journey where we calculate the fundamental group of the circle, and let's just say it's some generic base point 1, okay, but you know, any base point will do really. I want to say two things. Thank you to Black Pen Red Pen for this Laplace transforms hoodie. Thank you very much. It's really good, it's really comfortable and everything, and you know, if I ever forget a Laplace transform and I ever need to remember one, here it is, you know. And if all goes well and I manage to put an iCard in that area somewhere, I don't know, there will be a poll. You'll see the options. Vote, please do vote for one of those options, okay? If you're impartial, just do ip dip do. I do want there to be votes. I will be checking near the end of the week, and whatever is winning, I'll do. Okay. From now to then, I'll be doing a video on a reminder of some category theory and the Van Kampen theorem. Okay, and maybe one more video on algebraic topology. But we'll see how it goes in that poll. And we'll see what to do, okay? Now, anyway, the theorem that I'm going to be proving is that the fundamental group of the circle at some generic base point, let's call it 1, let's say 1 for now, is isomorphic to the integers, okay? Now the proof is, well, first we're going to define a loop, f sub n of s, and this is equal to e to the 2 pi I ns. Alright? Now observe, we see that f sub n is a composite of the map, which takes you from the map from I into the 1 sphere, which maps S to e to the 2 pi I s, okay, and the nth power map on the 1 sphere, okay? That's just an observation, right? And now we're going to construct a homomorphism. Right? So we define I of n equal to the equivalence class of f sub n, the loop, okay? And I will take you from the integers into the fundamental group of the circle. Alright, and it's very easy to check that this is a homomorphism, and the integers are, of course, the additive group of integers in this case. Okay, and it's very easy to check that this is a homomorphism, but I'm claiming that this is an isomorphism. And if it is, well then the proof is complete, of course. Because if this is an isomorphism, bap, they're isomorphic, boom, the theorem is proven. But this is the main part of the theorem, proving that this is an isomorphism. So I'm just going to write that I claim I is an isomorphism. Alright, so how do we do this? Well, the trick is to see that locally the circle looks like the real line. Alright, so we define P, which takes you from the real line into the 1 sphere, or the circle, defined as P of S equals e to the 2 pi I s. Right, now, observe, and now we know that this is a loop, which takes you counterclockwise, starting at 1, around the circle, okay? And each revolution is from the closed interval between n and n plus 1, okay? Now, we define a lift, okay? So we have a lift f tilde of n equal to n times s. Sorry, f tilde of s, f sub n tilde of s equal to n times s. Alright, and we observed that p compose f tilde equals f sub n. Alright, so when we compose these two maps, we get our loop, right? And that's very easy to check. Yeah, that's very easy to check. Right, so now, actually, this lifting here, which we have here, works in general, okay? So not only just in this example do we have a unique lift, but in general, okay, we have a unique lift. So this, as I said before, this path lifting works in the general case. So, say for example we have some path f, which takes you from the interval into the one sphere, alright, such that f of 0 equals 1, alright, then there exists a unique f tilde, which takes you from the interval into the real numbers, okay, such that f tilde of 0 equals 0, and p compose f tilde is equal to f. Alright, and why is this? Well, we know that the pre-image in R of some small connected neighborhood is in S1 is a disjoint union of a copy of that neighborhood, okay? Right, and in so let's just write some stuff down. Right, so observe that the pre-image in R of the pre-image in R of a small connected neighborhood, okay, in S1 is a disjoint union of a copy of that neighborhood. Alright, contained in the open interval about r plus n to r plus n plus 1 for some r in the closed, half open closed interval between 0 and 1. Okay? So we have this fact here. Now we can use the fact that I is compact. The interval is compact. Alright? Now, this means we can divide it into finitely many closed subintervals, sorry. Subintervals, okay? Now we have f which carries, okay? So f carries each subinterval into a small connected neighborhood. Alright, I'm just going to write it like this. Okay, into a small connected neighborhood. Okay, now, proceeding neighborhood by neighborhood, we observe that proceeding subinterval by subinterval, we observe that F is unique because each subinterval is uniquely determined by the lifting of its initial point. Okay, and I couldn't write it all down, but yeah, that's a QED moment if I've ever seen one. So the second part of the proof goes as follows. So say we have J, which takes you from the fundamental group of the circle at some base point 1 into the integers. Okay? Then we define J of F equal to F tilde of 1. So the end point of this unique lifting. Okay? Right. Now, we want to show, because this is going to be an integer, you can check for yourself this is going to be an integer. We want to show that this integer is independent of the class that we pick. Right? And the way we're going to do this is by defining a homotopy, H, which takes you from F into G. Okay? So we have F homotopic to G, and we want to show that the class of F is equal to the class of G, meaning that the class is independent of the integer which we choose, meaning that the whole proof will be complete, basically. Alright, how do we do this? Well, again, in a similar way, we have a unique homotopy, okay, H tilde. There exists a unique H tilde which takes you from the interval cross the interval to the real numbers, right, such that H of 0, 0 is equal to 0. Okay? Now, we define C of t equal to H of 0 t and the D of t equal to H of 1 t. Right? Sorry, H tilde of 0 t and H1 of tilde. Alright, again, by our formula, J of F sub n is equal to n. Okay? And we can check easily that G compose I, which takes you from the integers to the integers, is the identity. Okay? Now, if we have J of F, the equivalence class of F, equal to the J of the equivalence class of G, therefore, that would imply that the F tilde of 1 is equal to G tilde of 1, okay? Meaning that the equivalence class of meaning that the equivalence class of F tilde star G inverse tilde is equal to the equivalence class of C0, okay? And you can check the other way around for yourself by application of the induced homomorphism of P, okay, that the equivalence class of G tilde inverse star F tilde is equal to the equivalence class of C1. Therefore, F, the equivalence class of F equals the equivalence class of G, and the proof is complete. Oh my god! Yes! I did it! I proved that the fundamentals group of the circle is equal to is isomorphic to the integers, and now we'll look at some mathematical br applications. So these mathematical applications which I was talking about are quite vast, okay? And I'm going to provide you a two for this video, okay? The first one is Brouwer's fixed point theorem, but to prove Brouwer's fixed point theorem, we're going to use a little proposition, okay? Which I'm going to prove. Proposition. Alright, so there does not exist a continuous map R which takes you from the 2-disk into the 1-sphere such that we have R compose such that there exists an I such that R compose I is equal to the identity. And the way to do this is, well, we have the fundamental group. If this were true, if true, proof, if true, okay, we can factor this using the induced homomorphisms in the following way. We can factor this as the fundamental group of the circle at some base point 1, and this maps via the induced homomorphism via I to the fundamental group of the 2-disk at some base point 1, and that goes back to the fundamental group of the circle via the induced homomorphism by R. Okay, and this would be the identity. Okay, because remember that this holds. Okay, I forgot how to say it because I'm dumb. But yeah, anyway, this would be the identity. But this is the identity from the integers to the integers. But the identity homomorphism, okay, does not, the identity homomorphism of the integers doesn't, sorry, my writing's really bad, factor through the 0 group and you can check yourself that the fundamental group of the 2-disk is 0, is trivial. Therefore, we've contradicted this proposition. Therefore we've proven the proposition. Okay. Now we can use this result, which we got because the fundamental group of the circle is isomorphic to the integers, to prove Brouwer's fixed point theorem of dimension 2, okay? This actually works of dimension n with homology groups and stuff, but I haven't introduced that yet in the series, so we're just going to look at Brouwer's fixed point theorem of dimension 2, okay? So, what it says is, any continuous map F, which takes you from the 2-disk into the 2-disk, has a fixed point. Which basically means that there is some x such that f of x equals x. Alright, how do we prove this? Okay, the proof actually follows from the proposition quite nicely. Assume it's not true. So assume that f of x never equals x. Okay? Now we can define R of x is equal to the intersection of the 1-sphere with the ray that passes through f of x, okay, and goes to x. I think it starts at f of x and goes to x, but never mind, okay. Now, we see that r of x does certainly equal x in the one sphere, okay. However, now, when we writing r in terms of f, now r is certainly continuous, and r compose f would be in the identity because r of x equals x in the one sphere, but that contradicts this proposition. So we've just proven, using the fundamental group of the circle, Brouwer's fixed point theorem of dimension 2. Now, to finish off the video, we're going to prove the fundamentals theorem of algebra, which might come as a shock to some of you, because usually algebraic topology is algebra serving topology. But in this case, we are actually going to use the fundamental group of the circle to prove the fundamental theorem of algebra, and compared to the complex analysis method, this is very simple, okay? So, here we go. We proceed to prove the fundamental theorem of algebra. Again, surprisingly, we use the fundamental group of the circle to do this. So, first we have to define what the degree of f is. Right, so let L in the fundamental group of the circle, some base point 1, be a generator. Okay? Now we define the degree of f, okay, as follows. So we have the fundamental group of the circle, okay, and that takes you via f star to the fundamental group of the circle at some base point f of 1, okay, and that takes you via gamma of the equivalence class of A to the fundamental group of the circle as at the base point 1, and gamma of A times f is equal to gamma of A star f star A inverse. Okay? Now, the degree of f is defined as L to the degree of f times L. Okay, and important facts to know are that the degree of f equals 0 if f is homotopic to the constant map, and if f sub n is equal to x to the n, then the degree of f sub n is equal to n. Okay? Now we can use this to prove the fundamental theorem of algebra, which says that if f of theorem which says that if f of z is equal to z to the n plus a sub n minus 1 z to the n minus 1 plus all the way up until a sub 0, okay, well then we have f of z equal to 0, okay, then there exists a z such that f of z equals 0, unless n is equal to 0, okay. So let's assume it's not true. So this would allow us to define f hat of x equal to f of x over the magnitude of f of x, okay? Now, we want to calculate the degree of f, okay? So assume that assume that f of x does not equal 0, okay? Right, now, if the magnitude of x is less than or equal to 1, that means that we have h of xt equal to the magnitude of f of xt, equal to f of xt over the magnitude of f of xt, okay, which is a homotopy from this to the constant map f of 0 over the magnitude of f of 0. And because this map is constant, this means that the degree of f hat is equal to 0. Now, we let the magnitude of x be greater than or equal to 1. This way, we can define, let's say, kj of xt equal to k of xt over the magnitude of k of xt. Okay, and now k of xt is defined as t to the n f of x over t. Okay, and now we can deduce that this is homotopic to f sub n, right? Okay, and this implies that the degree of f hat is equal to n. Now, the degree of f hat is equal to n, the degree of f hat is equal to 0. This must mean that n equals 0. So the only polynomials with no roots are constant maps. QED. Okay, hopefully you guys enjoyed this video. As I said, hopefully I can put an iCard up in the top left up there. And thank you once again to Black Pen Red Pen for this t-shirt. And yeah, next video we'll be looking at a reminder of some category theory and Van Kampen's theorem. See you then. Bye.